you all for another presentation on electronic devices and circuits. By the way, I am Srinivas presenting you on various subject related presentations on various engineering subjects. Right now we are discussing about the electronic devices and circuit subject, which is one of the core and very important subject as far as the electronics and communication branch is concerned, right? And so far we have been discussing about the various biasing techniques of transistor, right? So the theoretical part we have covered regarding the various biasing techniques of transistor. So in which we have seen the fixed bias configuration as well as the self bias configuration, and then the collector to base bias configuration. Even we have seen some examples on fixed bias as well as even collector to base bias, right? Let us discuss in today's presentation about how the stability factor of the given self-bias circuit is obtained, right? So today I am going to give you a very important model question that is expected in GATE as well as UPSC IAS examination with respect to ECA students. Let us go into the, problem solving part of it, right? Let us see the example on the self-bias configuration of a transistor. So this is the given problem which is based on self-bias configuration. If the transistor, okay, is connected in this fashion, right, with emitter resistor parallel with the emitter capacitance, this is something CE, this is called as C suffix C, emitter capacitance. Similarly, collector resistor RC, even R1 and R2, right? So here the plus VCC is given, it is 22 volts, and then the input voltage we are applying at base, and then the output we are taking out from the collector terminal, right? So for this given circuit, you are asking to find out what is IB, what is IC, what is VCE. These are the things or parameters that are being asking for this problem, right? So remember that if the transistor is given in this configuration R1 and R2, RC and then RA, simply you can say that or remember that it is a self bias or emitter bias or voltage divider bias, even called as, okay, universal bias. Those are the different names for this circuit actually. Clear? Now, so very quickly we can try to solve this question, right? So to find out IB, I think the theoretical part, what are the expressions associated with this circuit, means that by applying KVL at the input junction of the transistor as well as by applying the KVL at the output junction of the transistor, what are the expressions will come out for this circuit or for this configuration that I have already explained in our previous presentations. There you can see, okay, you can go through that. So now directly I can give you the expression because it is the collector, the connection where I can assume it as some voltage, base voltage VB. However, I already told you in previous presentation that this is the analysis for solving IB and IC and VCE. This is comes under DC analysis. So while discussing about the DC analysis, forget about the consideration of this capacitance. CC means it is a coupling capacitor which will be used both at the input side as well as the output side actually. So CC will not come into the picture, even your CE also will not comes into the picture. So okay, you can directly ignore these capacitance and you should concentrate on this transistor, the resistances and then the supply voltage. That's it. That's it. From these given values and from the beta also, beta is given 100. With these parameters only, you can directly solve these parameters actually, right? So what I need to do, first of all, this is the IB, nothing but the current flowing through the base terminal. This is IB actually. This is the base current which flows through this base terminal because it is a base actually. This is the collector, as you know already. This is emitter. Therefore, IB is the base current flowing through the base terminal, and through this RC, your collector current will flows actually, right? And what is VCE? VCE nothing but the voltage across between collector to emitter actually. That is the voltage between collector and then emitter actually. Is it clear? Now, how to solve these parameters? So directly and quickly I will explain you that. So at this particular point, by applying your voltage divider formula or potential divider formula, so you can write the expression for VB. So what is VB? VB nothing but the voltage across your resistor R2. Therefore, how the VB can be calculated? So using your potential divider formula, VB can be calculated as VB is equal to input voltage. Okay, so input voltage I can write to that. V input or supply voltage you can say. Okay, supply voltage or input voltage into the resistance where you are taking out the potential. I mean nothing but the VB. Where you are taking the VB nothing but the voltage across the R2. Therefore, the resistance R2 by the total resistance nothing but R1 plus R2. That's it. So this is the resistor where I am finding out the value of VB. This VB nothing but the voltage across R2. Therefore, VB is equal to this resistance by total resistance R1 and R2 into input voltage. Your input voltage is nothing but plus VCC. So this further I can write it is V in nothing but it is plus VCC. It is R2 by R1 plus R2. Clear? And further this can be, what is VCC value? You can you can substitute the given parameters. It is 22 volts by what is R2 value? R2 is 3.9 K. 3.9 into 10 power 3 by what is R1? 39 K. It is 39 K plus 3.9 K. You can simplify with your calculators. You can simplify with your calculators. There you will get your VB value is something, you will get 1.99 volts you will get. This is what the first parameter which we need to find out. Okay now. This is what actually VB is equal to 1.99. This is the simple formula which will be used to find out VB, right? Then, so further this circuit can be simplified as, so I can remains the same, this circuit as it is, and just see how I can going to simplify this circuit for our finding that for IB. The same circuit actually, the same circuit, right? So here, let us see how I can use. So this is, I can put it as RB here, and this is my VB now. Okay, and this you can connect to even this terminal. Everything can be grounded, no problem. Everything will be grounded. Right? This is what your VB. Now it is plus and then minus. This is what your RB. Now your current flows, your IB flows through this actually from the supply voltage. This is now simplified circuit diagram. So what is your VB? It is 1.99 volts. So means your 1.99 volts will be applied here. What is RB? RB is nothing but, remember, RB is nothing but it is parallel combination of R1 parallel with R2. Your RB is nothing but parallel combination of R1 R2. So what is R1 value? It is 39K. It is 3.9K. Let us take the parallel combination. So your RB is equal to, what is the parallel combination? R1 R2 by, it is R1 plus R2. So means that you can substitute that from your calculator, right? You can substitute that from your calculator. You can get the error, you can arrive the value. So this is the formula you should use. R1 R2 by R1 plus R2. That gives your RB, right? So directly I can go to calculate IB value actually. So for that I need to write the KVL. That is what very important. So base to emitter I have the internal voltage also. It is base to emitter. Internal voltage will be there actually, right? So it is plus and then minus. Therefore write the KVL expression here in the input. This is what now your input loop. Therefore write the KVL equation Therefore, VB is equal to what I can write? IB into RB plus VBE plus IE into RE. IE into RE. Now, is it not? So, IE into RE. Therefore, from this, there is a relation actually. There is a relation actually. What is that? What is that? What is that? So, here IE is equal to, this is the equation, first equation which you should use, and IE is equal to what actually? IE is equal to IB plus IC. Is it not? IE is equal to IB plus IC. And further you can use the relation. What is the beta actually? Beta is equal to your output current by input current. No? And from there, what is IC? What is that IC? IC is equal to beta times IB. IC is equal to beta times IB. Therefore, substitute that IC value here. IC is equal to beta times IB, right? And this is equal to, it is IB plus beta times IB. Therefore, beta times IB. Therefore, you can take IB as common, 1 plus beta. This is what your IA. Right? Right? Therefore, now I can remove this, I can erase this so that you can understand very well. I can write that expression here. I can write the expression here, right? So it is V out, already I have given in the circuit, no problem. Therefore, from here, your VB, VB is equal to what? IB into RB. Therefore, at this place, for IE, you write this one. IE is equal to IB times 1 plus beta. Therefore, take IB as common there. From here, IB, from here, IB if you take. Therefore, if you take IB as common, then what you will get, RB plus, then here you will get, what you will get? From here. So, 1 plus beta times into RE means 1 plus beta times RE you will get. Clear? Plus VBE. Plus VBE. Am I clear? This is equal to, you write expression for IB. IB is equal to now VB minus VBE by RB plus 1 plus beta times what? RE. So, this is the expression you should use for IB. Now, all parameters you know. All parameters you know. All parameters you know. Is it not? Is it not? So, therefore, you substitute for IB. IB is equal to, normally you will get something. You will give the value. IB is equal to how much you will get? It is something 0.00, some 85, something like this. Some milliamps you will get. Okay. This is what normally your IB actually. Is it not? This is what your IB value. This is what your IB value. You can calculate from you can evaluate this value from your calculator. And now this is IB. And from this, IC is equal to what? IC is equal to beta times IB. Beta times IB. What is beta? Beta is equal to 100. It is 0. Substitute that IB. Therefore, what will be the value? Multiply that with 100. Then IC is equal to something you will get 0.85. 0.85 milliamps. 0. This is what your IC. 0.85 milliamps. Right? So, this is what the collector current. And similarly, now coming for VCE, what is your VCE? Is it not? So, your VCE is equal to how? The VCE. For VCE, write the KVL expression for output loop actually. Write the KVL expression for output loop. Output loop is equal to simply this one only, plus VCC. Therefore, VCC is equal to IC into RC, IC into RC plus VCE plus same IA into RE. So IE into RE will be common for both the input loop as well as output loop. Second equation. So from this directly, same way what we have done in the first step, same here in this IE, right? What is that? IB plus IC. Or from there you can write 1 plus beta times IB. Is it not? You know everything. So from this directly I can write the expression for VCE is equal to VCC minus, write everything then, IC into RC minus IE into RE. You know everything. You know everything. So VCC is your 22 volts minus IC, already we have obtained now 0. something 85 milliamps. RC nothing but your 10 kilo ohms. Is it not? You know everything from the circuit. IE is equal to 1 plus beta times, okay, 1 plus beta times into IB, RE nothing but 1.5 kilo ohms, right? So if you substitute all those things, no, you will get your VCE something, how much, you know, it is something, your value is 12 point, approximately you will get this much voltage. You will get 12.21 volts normally, your VCE. So this is how we have to calculate the values, either base current, collector current, VCE. Is it not? Remember that I already told you that the value of VBE, and assume that as it is a silicon transistor, your VBE is equal to treat it as 0.7 volts. This already I have told you in the previous presentation while solving the problem, right? So I hope that you understood well this problem, and right, we will see some more problems in the subsequent presentations. Hope you understood very clear, and if so, please do not stop to give you your positive feedbacks and then observations, and do not forget to share this information to your friends and colleagues, right? And with this I will finish up this presentation, and we'll meet in the next subsequent presentation. Thank you. Have a beautiful day.